computer audio, start video. Julian is with us. Okay, today is Thursday, October 22nd. And let's see who we've got here. Oh, we've got Ashley, Ben Seaman, and Julian DiCarlo. Welcome, you guys. Hello out there. Yeah, we're a little early. We're 3 minutes early. But I can answer a question if you have one. How about it, Julian? Do you have any questions for me? Julian doesn't have anything. How about Ben? Do you have any questions for me, Ben?
Good morning.
Good morning.
None so far.
None so far. Hey, I went outside to feed our dog, and it's warm and nice out there. And just a lovely day out there. I was kind of surprised. I thought maybe the cold weather it was on us, but it's still pretty pleasant out there. Well, how about Ashley? Do you have any questions, Ashley?
No, I don't have any questions.
She's all right. Okay. Well, what are we going to do today? Let me look and see here. Let's see. We're studying bending moment and bending moment diagrams. That's what we're doing. Let me do one. This is not on your homework, but I think it would be fun for us to go through for practice. And then I want to talk to you about the flexure formula. So the topic today is bending. And we'll be studying bending diagrams and bending stress and, well, bending strain. Where there's stress, there's strain. And I think I've told you guys this before. If you have a beam and you support that beam here like so, we're supporting the beam there, and then somebody comes along and puts a force on it. That's what usually happens. See, your house or your apartment has these beams underneath the floor that's holding the floor up, and then you've got furniture and refrigerators and people and desks and couches. And you know what? That beam kind of sags just a little bit. Here we'll draw it with a bigger sag here. See that beam. Now I'm exaggerating this so that we'll understand. But look, that beam is it's kind of got a sag to it there, doesn't it? So you put forces on here, and it bends like that. Well, did you know that the top of that beam has compression and the bottom of the beam has tension? It's actually being stretched. Does that make sense that the bottom of the beam is being stretched a little bit and the top of the beam is being compressed? Well, what happens right here in the middle? Right here in the middle of the beam, you don't have any compression or tension. See, it's compression above that. They call that the neutral axis. That's the neutral axis. Now, this beam may be of many types. It might just be a rectangular type. Here, we'll draw you a cross-sectional picture there. There you go. There's your beam. See right here, right in the middle, they call that the neutral axis. And above the neutral axis, you have compression. And below the neutral axis, you have tension. But right at the neutral axis, you have neither one. There's no stress and there's no strain right there at the neutral axis. Now, if you're in the elastic region, this neutral axis coincides with the centroid. See, there's different kinds of beams. You might have a beam like this. There we go. There we go. You might have a beam shaped like that. They have a name for those kind of beams. They call them wide flange beams. Or you could say it's a T shape. But on that particular beam, lost my train of thought there. The centroid is kind of moved up a little bit. It's kind of right in here someplace. It's not halfway from the top. It's a little bit closer to the top. Does that make sense? The centroid would be a little closer to the top. Well, see, that's where you would have your neutral axis. I'll just abbreviate it NA. There you go, neutral axis. Well, everything above that neutral axis on a beam that's got sag to it like that would be compression. And everything below the neutral axis would be tension. There's just all kinds of different beams. Here's one here. You could have a triangular shaped beam. That's possible. Yeah. You could have a triangular shaped beam. Well, you guys studied triangles and you know that the centroid of the triangle is 1/3 of the way to the top. See, if you'll take and divide by 3 there, right there is that's your neutral axis. Everything above that neutral axis, maybe I made that too low. I don't know. It's more like maybe like that. There you go. Everything above that neutral axis is, well, it's either tension or compression. We'll ask one of my excellent students. Let's see here. Oh, we got some more scholars that are clocking in here. We got Shane, Samuel, Nicholas, Mohammed, Julian, Ashley, Alex, and Ben Harris. Good crowd. Let me pick on Ashley. She's a good sport. Ashley, unmute and say hello, please.
Hello.
Now, Ashley, what I want to know is if you had a triangular beam that was loaded like this, what do you have up here? Is it compression or tension?
Compression.
You got it. You got it. It's compression up there. But it's tension. It'll be tension down here. Very good. She's listening. We're learning. Good deal. Well, that was kind of fun. We're going to do a beam or a bending loading diagram now. But is there any questions? Are there any questions before we do our beam or our bending loading diagram? Oh, okay. All right, I wanted to do this problem here. This is problem 641. 641. It's not on your homework, but I think it'd be good for us to do it. Okay, let me find it here. Okay, 641. I found it. It's on page 288. Okay, you know what you're supposed to do. You're supposed to draw the free body diagram. All right, here goes. Free body diagram. Free body diagram. And then they've got a hinge right here. This beam is made of actually two parts, A and B. Try to draw that better, maybe. There you go. There's A, B, and then B, B, C. It's got two different parts there. And this is, well, there's a force right there. There's 600 newtons. Let me put that in. .600 newtons. And then there's 2 meters here, 2 meters here, and 2 meters here. And you have a distributed load. There's a distributed load right here of 400. I think they use a little W for distributed load. Newtons per meter. Okay. Well, that's everything. Oh, wait a minute. No, I got that right. That's what they call a fixed connection there at the wall. And now the next step, well, we drew our free body diagram, but we have to put all the external forces and couples acting on it. Now, this here, 400 newtons per meter for 2 meters. You know what that makes? That makes 800 newtons, doesn't it? See, we've talked about that. The resultant is the area of your distributed load, and it's a rectangle, and the area of a rectangle that's the resultant. And it's equal to the area of that rectangle, which is the base, times the height. Hopefully this is very boring because you understand it so well. And so that resultant force is 800 newtons. 800 newtons. Now at A and C, we can have some forces. Since C is a roller, the only force you can have is some force going up, and we'll figure that out in a minute. And then here at A, well, I think you're going to have a force going up for sure to support that. But see, since you've got a fixed connection, I think you're going to have an external moment. Why don't we label it M sub A would be a nice name for it. So now we've got all the red stuff on there. Any questions so far? Okay, well, what's the next step? Well, we have to find these unknowns. These are external forces and moments acting on the body, and we have to find them. Well, here we go. Let's try to find them. Now, what we're used to doing is the sum of the forces. Let's talk about the y direction because there are no forces in the x direction. The sum of the forces in the y direction would be this one. Why don't we call it A? So we have A minus 600 minus 800 plus C equals 0. Well, we can't solve that because it's got two unknowns. Well, let's do the sum of the moments of maybe about A. That'd be good. Now that moment there you have to include, it's an external moment about A, and we don't know what it is. This force going through A doesn't give you a moment, so we don't need it. But you're going to need a negative 600 times 2 meters. Now we're going to ask one of my students, how come that moment is negative? We're going to ask somebody here. Alex, unmute and say hello, please.
Hello.
Hey, Alex, how come that moment there, that 600 newtons times 2 meters, how come it's negative, Alex?
It's going clockwise around A.
You got it. He understands. It's clockwise. Clockwise moments are negative. Counterclockwise moments are positive. Now then you have a minus 800 times, well, it would actually be 5 meters, wouldn't it? And then you have plus C times 6 meters. And Alex knows why that's a plus, because it's counterclockwise. And that's equal to 0. And now let's look and see what we have. Well, we have 2 equations, but we have 3 unknowns. kind of up a creek. 2 equations, but 3 unknowns. Do you guys know how to proceed? I'm opening it up to you. I'm listening. What do you do now? Because see, you can't solve those equations. There's 2 equations, but there's 3 unknowns. Look, A is an unknown, C is an unknown, and this M sub A is an unknown. And the C is an unknown. You can't solve 2 equations with 3 unknowns. So I'm listening. Do you have any suggestions? Well, I didn't hear anything. Let me ask some specific students here. How about my friend Ben Seaman? Ben Seaman, unmute and say hello, please.
Good morning.
Hey, Ben. Hey, Ben, look, we got 2 equations, but we got 3 unknowns. Do you have any idea what we can do to solve this?
I'm not sure, but I did have a question of why the moment about A is involved in that equation. Because isn't it basically going through a point A, so it's canceled out or not part of it?
The moment it cancels out, but this is a force. There's a force going up. We don't cancel that out.
I'm talking about the moment equation. Why MA is in there.
The A goes through point A. See, here's point A right here. Da-da. And the force there goes through point A. It does not give you a moment. Does that make sense? Forces.
I was asking
Go ahead.
about the MA, the moment about A in the equation for the moments.
The EMA. You're talking about this.
Yeah, why is it involved in the moment equation at all?
It's a moment. It's called a couple. Actually, here, let me draw you a we'll take a zoom photograph of this here. What I've done is I've got my camera in here and put it on magnify. And what you have here is you have a you have a force distribution. It's kind of like this. It's a force distribution. And I'm talking to my friend Ben right now. And this is provided by the fixed connection. Now you can have that by, it could be glued, or you could have brackets there, you know, like some metal brackets that's bolted into the wall. There's different techniques. Nails would probably come loose, but or it could be a weld. If you got metal here and metal here, you could weld that. Put a little weld here on each corner. But see, this weld here is providing tension on the top of the beam, and this weld here is providing compression. That's a fixed connection. Fixed connections can provide not only forces, it's providing a force, all right, there's a force going up, but it can provide moments also. And the moment has come from this distribution that I tried to draw. I don't know, Ben, I tried to explain it. Did that make a lick of sense?
It makes more sense now. Yes, thank you.
Yeah, anytime. Just ask. Okay, well, we still are stuck now. We've got 2 equations and 3 on.
Mr. Griffin?
Let me go to my friend Darren. Darren, unmute and say hello, please.
Hi. I honestly have no idea. I'm sorry.
That's okay. That's what I'm here for. See, if you guys knew all this stuff already, I wouldn't be needed. Hey, look, we all want to feel needed, right? Does anybody out there know what to do? Because see, we have 2 equations, but we have 3 unknowns. I'm listening.
Mr. Griffin?
Yes. Mohammed,
Don't we have to put an external force on the point B?
Mohammed is talking about point B. And what about point B? I didn't quite understand, Mohammed.
Don't we have to put an external force on the point B going upward?
There is no external force on point B, Mohammed. No, I don't see any external force, do you?
No, I'm saying, do we have to like put it like there, because there's a
Yeah.
point over there?
Mohammed, you can't just manufacture external forces out of thin air.
Okay,
There's no
that's fine.
external. Look at the problem. This is problem 641. They have a 600 Newton external force, and they have this what they call a distributed force. Now we know there has to be these three here, but there's no external force there. See, this force, Mohammed, this force comes from that roller. Rollers can push up. This force comes from that fixed connection. Fixed connections can push up. Not only that, fixed connections, you know what I'm saying? I'm saying fixed connection. That's what that is. It's a fixed connection. I know where the force in the moment's coming from. It's coming from a fixed connection. But at point B, Mohammed wants me to put an external force there, but external forces have to come from someplace, and it's not coming from someplace. See, this external force is coming from that roller. This external force and moment are coming from that fixed connection. But there's nothing there. And so there's no, Mohammed, I'm sorry, but there is no external force at B. But thank you for asking. Okay, the floor is open. What do we do now?
Can you take a moment at C?
Take a moment at C. And now who was that,
Yeah.
please?
Shane.
Shane? That's my friend Shane. Shane, we're going to do it. Here we go. We're going to take them. Shane has an idea. We're going to take the moments at C. Nothing wrong with that idea. We'll do it. Here goes. Well, that force here doesn't give you a moment because it goes through C. But this one does. The 800 newtons times 1 meter in this case. It's positive, Shane. And he knows why. Shane, how come it's positive? How come that moment's positive?
It's counterclockwise.
Yeah, he knows. Plus the 600 newtons times 4 meters minus the A times 6 meters plus, don't forget that MA, we can't just forget it. So, hey, look, we got another equation. Hey, we got 3 equations and we have 3 unknowns. But it's sad, but that didn't help any, because in mathematics, you have to have independent equations. If you can solve 3 equations with 3 unknowns if the equations are independent. Ask your math teacher about that, but this equation isn't going to help us. You can play with these 3 equations all day long, and you'll never, ever find the unknowns.
Mr. Griffin?
Yes, I'm listening.
So what if we divide this, if we section the beam and find the moments at like that?
Yes, that's what you have to do, Mohammed. That's exactly what we're going to do. Well, let me get rid of this last equation. That was a great idea, though. There was nothing wrong with that idea. But what we're going to do is we're going to divide the beam, and we're going to just look at this part right here. We have this distributed load. We have our force at C going up. We don't know what it is. Now, there is a force here at B, but it's not external. It's coming from AB. I think AB is giving a force that's going up, but it's not external, it's internal. And see what you got here is, what did we say, 800 newtons? Okay, now what? Well, what we're going to do is we're going to take, did you know you can take the sum of the moments about point A like we did, or point C like my excellent student suggested, or you could take the sum of the moments about B if you wanted to. We haven't done that yet. We haven't taken the sum of the moments about B. Now B is a smooth pen. It can't give you any moment itself. However, these two can. And the sum of the moments about, now B can have forces, but the forces going through B doesn't give you any moment about B. Do you understand? Any force going through a point can't give you a moment. And the pen is a smooth pen, so it can't give you a moment. Smooth pens don't twist. It's kind of like if you grease your doorknob. Get some Crisco and grease up your doorknob and then try to turn your doorknob. It's kind of hard to do because smooth pens, you can't get much twisting going on. But here we go. We're going to take the sum of the moments about B, and what we have is C times 2 meters. That's positive. Minus 800 newtons times 1 meter equals 0. Hey, we can get C now. Can you see what C is? C is going to be 400 newtons. We just figured out C. It's 400 newtons. What we did was we followed Muhammad's suggestion and we broke this thing into parts, and we just looked at this part BC, took the moments about B, and I don't care what forces are acting on B, doesn't matter, they go through B, and B can't give you a moment like this fixed connection can. See, that's not a smooth pin. If that fixed connection was a smooth pin, you'd have to erase that couple. You can't get a couple acting there if that was a smooth pin. Okay, well, we made a lot of progress. Now, if you know what C is, hey, we know what C is, it's 400. I can solve for A. Okay, I could almost do that in my head. 600 and 800 make negative 1400, plus C would make a negative 1,000. You know what I think? I think A is 1,000. I think A is 1,000. Try it. 1,000 minus 1,400 plus 4. Yeah. We just figured out what A is. See, A is 1,000. Got it. Now what? Well, now that we know what C is, we can get this couple at A. Here we go. If C is 400, get your calculators. I'll give you a minute. I want you to solve for the couple, the moment acting at the fixed connection. I'll be quiet. Okay, I found what the external couple, the external moment acting at A is. Let me go to one of my excellent students here. Samuel, unmute and say hello, please.
Hello.
Samuel, have you plugged in this C, which is 400, and solved for that external moment?
I got 2,800 Newton meters.
That's what I got. I got 2,800. Good going, Samuel. Newton meters. Hey, we got it. It's 2,800 Newton meters. Well, now we're ready to start our problem. See, what they wanted was the shear loading diagram and the bending moment loading diagram, but we had to go through all of that just to get these red things, but we got them. And you understand it, right? Are there any questions? Well, I guess you understand it. Okay, well, let's do our loading diagram. See, we're supposed to make loading diagrams. So let me make some room here. And don't forget to put units in. I didn't put the unit in on that, did I? It's 1,000 newtons going up there. So you got 1,000 newtons going up, 400 newtons going up. That makes 1,400 newtons going up. You got 600 newtons going down, 800 newtons going down. Well, that makes 1,400 newtons going down. That's good. 1,400 going up, 1,400 going down. That makes sense. Okay, now we're going to do the shear loading diagram and the bending moment loading diagram. Okay, well, let's see. If you section this real close here to the fixed connection, can you see that you would have to have a shear force going down of 1,000 newtons? Well, shear going down on the left-hand member is considered positive. So you got a positive value of shear, 1,000 newtons. In fact, I think that 1,000 newtons stays 1,000 newtons all the way to here. And then it drops down 600 to 400 newtons. Now, if you don't like the way I did that, you could take a section in here. See, if you sectioned it in here, if you have 1,000 going up and 600 going down, don't you have to have 400 going down? Well, 400 going down, let me remind you, if you have a shear force going down on a left-hand member, it's considered positive. So what we got here is we've got 1,000 newtons of shear that's positive. Then we have 400 newtons of shear that's positive. And then what happens is we got this distributed load. Now you can use an equation that goes like this. There's an equation in your book. Remember, there's one way of solving these is to use the equations. See, what this is the integration form of this equation here. If you take this equation and integrate it, you'll get that equation. If you take this equation and differentiate it, you'll get that equation. They're like brothers, okay, or sisters. They just, it's like multiplication and division or addition and subtraction. They say the same thing. But see, that's equal to the area. We learned that in calculus. Well, the area of this is the base times the height. We did that already. It's 800. So we have to go down 800. And if you go down 800, that's going to put you at, there you go. It's going to put you at minus 400 newtons. And then when you get there, it pops up. Now, this is one case where you can draw that line and go back up to 0 if it makes you happy, because you have a 400 Newton force that brings it back to 0 there. Well, that's it, guys. We just did the shear loading diagram. They call this the shear loading diagram. The full name is the shear force loading diagram. Ta-da, there we go. We just did it. And if you want to make it pretty, so you can color it in, get yourself some Crayolas there, and you can make it pretty. What do you think? Yeah. Color it in there. We got ourselves a shear loading diagram. There it is. Pretty neat. Now we're going to do the bending moment loading diagram. This thing here is going to be the bending moment. Loading diagram. Well, if you come over here to this fixed connection, there's an external moment that's going, what do they call that? Counterclockwise. So inside this beam, you're going to have an internal bending moment that's going clockwise. Well, that's negative. Clockwise is negative. So what you got here is you got a negative, what do we say, 2,800? We got negative 2,800. Does that show up? No, I'm off my, I'm going to have to move it up a little bit. I think you can barely see it there. I've got a negative 2,800 Newton meter bending moment acting at A. And then what happens? Well, how's the equation go? It goes like this. So the shear is 1,000. That's positive. So that means the slope. That means slope. Derivative means slope. That means the slope is positive. So we're coming up here. Tell you what. Let me fudge this a little bit. I kind of edged myself out of any room there. And I need the room. And so what we've got here is a negative. I could go even lower than that. I could come down here. Here we go. Here's the negative 2,800 Newton meters. And I'm right here. And I've got a positive slope, and it's coming up here like this. But where do I go? I don't know. I don't know how far to go. Well, I'll tell you how far to go. If you integrate this, what you get is this. These are your four equations that we talked about. You know what that is? That's the area. This area here, you see it? This rectangle, it's got a base of 2 meters and a height of 1,000 newtons. Well, 2 times 1,000, that's 2,000. You know what? This comes up here to, I'll tell you where it goes. It comes up to minus 800. There we go. That value right there is minus 800 Newton meters, because see, the area of that's equal to area. And I'm getting 2,000. 2 meters times 1,000 gives you 2,000 Newton meters. Does that show up? Yeah. So if you increase your bending moment by 2,000, if you're at negative 2,800 and you add 1,000 to it, no, you add 2,000 to it, I think you get to negative 800. Yeah, that's right. Then what? Well, look at the area under this right here with me. It's a rectangle. It's got a base of 2 meters and a height of 400. So that's 800. You know what? If you add 800 to that, that'll put you right up here to 0. Here you have it. There you go. Hey, it's 0. Well, you know, that makes sense because you can't have any moment provided by a smooth pen. We could have put that 0 right there where B is a long time ago, because we know smooth pens can't give you any moment. Now, what do we do in here? Well, good question. Now, why don't we use this equation here and we'll solve it. There we go. What we need, though, is we need the equation for this shear force. Now, here's my plan. You guys all know there's a thing called the slope-intercept method. They teach you in school. It's called the slope-intercept method. They still teach that? See, let me ask one of these excellent students. Darren, unmute and say hello, please, Darren.
Hello.
Darren, do they still teach this thing called the slope-intercept method of drawing straight lines? Do they still do that?
They did when I was there.
Yeah, there you go. Hey, Hey, Darren, they did that when I was there.
Hey, nice.
Now, let me see, when was I there? Let's see. I was there 60 years ago when they did that. When I was taking that class, that was 60 years ago. And isn't it nice that some things don't change? What that is, it's the how to graph a straight line. Well, we got a straight line. Do you see this right here? This is a straight line. See it? And we're going to use the slope-intercept method. Well, I know what the slope is. The slope is, well, it's negative 400. See how these are all going down? They're not going up. So I'm getting mixed up now. Yeah, now the shear force is going to have a slope of negative 400x. mx plus b. There you go. mx plus some b. Now what b would be is the y-intercept. The slope-intercept method has to have well, that y-intercept would be way the heck over here someplace, but I can get it. I can just plug in any points that I know, like this point right here happens to be 400. So I'm going to plug in 400. And x right there happens to be 4. So I'm going to plug in 4. This may not make any sense to you. But what I come up with for my b then is, can you read my writing? What I come up with for my y-intercept is trying to do that in my head. Probably should do it on my calculator. I'm getting minus 1600. That makes it a plus 1600. And then you add 400. I'm getting 2000. So I think I have the equation for this line. Here it goes. We'll see if it works. We're talking about this value of shear for this line here. I think it's minus 400x plus 2000. I'm going to need that to plug it into this equation. Now let's see if it works. Now when x is 4, you get 400. Well, that's good. What about when x is 6? Plug in 6 and let's see what we get. Well, we'll get, let's play, 6 would be right here, wouldn't it? But it's, you know what you get minus 400. That's good. Now here's the thing, plug in 5. You know where this is? That's at 5. Plug in 5 for x and you get 0. Yeah. So you plug in 5 and the shear is 0. That's it. That's the equation. Now, once you have that equation, we can integrate this and get our bending moment in there. So let me do that. I just need the room here. I got a little room right there. That'll work. The change in your bending moment is going to equal the area. And now we're going to go from 4 to whatever value of x you want in here, times v, which is minus 400x plus 2000. All right, now here we go. This is the final value of m minus the initial value of n. Well, the initial value of n for this line right here is 400. So you'd have to subtract the initial value. And then when you integrate this, you'll get minus 200x squared plus 2000x. Now, did I lose anybody? Oh, wait a minute. Auga, wait a minute. I have to subtract. You have to plug in the 4, and you'd get, maybe I should write it out. I can do it in my head. 4 times minus 400 is minus 1600 plus 2000. I think it's 400. Can I fit that in here? Okay. All right. Well, let's write the value for our bending moment. I'm going to add that 400 in here. I wonder if I did that right. And I'm getting this here. I might have made a mistake, but we'll check it. See, when you add that 400 on the right, that minus 400 goes bye-bye. Well, let's see if this works. When x is 4, when you plug in 4, what do you get? Let me see. Let me see what I get. I think I made a mistake. No, I made a mistake. Now, just a minute. I think I got this equation right, but I'm going to double check it. Now, when I plug in the value of 4 meters, that puts me right here, 4 meters. What I get is minus 1600 plus 2000. I get 400. That worked. That's a correct equation. When I plug in 5, I think I get 0 because 400 times 5 is 2000 negative plus, yeah, that works. And when I plug in 6, I get minus 400, and that's good. Yeah, this is a correct equation. Now let me see if I must have fouled up on this moment equation. The change in your bending moment, we're going to go from 4 to any place in here, is negative 400x plus 2000. That's right. And now we're going to go, the change in your bending moment is final minus the initial. It's 400 to start with. That's right. Equals, now when you integrate this, you get minus, minus 200x squared, that's right, plus 2000x. This must be where I made my mistake. Look at guys, you have to put in 4 here and x here, and this must be where I made my mistake. Let's see. Okay, now when you put that 400 over there, you get 400 minus 200x squared plus 2000x. But then see, you have to subtract. When you plug in the 4, you got minus 200 times 4 squared plus, I'm running out of room there, 2000 times 4. Don't you have to do that when you do limits? Don't you have to subtract something? All right, let me see what we get when we do that. Here goes. Okay, here's what I'm coming up with. I'm coming up with m equals minus 200x squared plus 2000x. And there's a plus 400, and what this amounts to is 4800. So you have 400 minus 4800. That's minus, I think it's 4400. Isn't that right? Take 4800 negative plus 400. Yeah, that's right. Now let's test it and see if it works. The bending moment when x is equal to 4. Plug it in and let's see what happens. I'm getting 400. Well, that's good. Because see, when x is equal to 4, wait a minute, somebody wants me on the phone. Oh gosh, who was it? Oh. Hello. If they don't answer back, it's one of those robots. I don't want to talk to a robot. Okay, now I'm getting mixed up here. I'm trying to find, it should be 0. We should get 0 when we plug in 4 meters. So anybody know where I made my mistake?
Sir, I think that in the change of m, you shouldn't put it m minus 400 because if you see you start at 0 at b.
Oh, yeah. Now, who was that?
Oh, this is Samuel.
Samuel, you get a honking big fat thank you point, Samuel. The bending moment here is not, I was putting in the 400. That's not right. The bending moment is 0, like Samuel is trying to tell me. See it there? It's 0. That there is 0. Thanks to Samuel, I'm going to have the right stuff now. That's just a 0. And so you get this here. And then this here is minus 4,800, I believe. Okay, now we're going to try it. Plug in 4 meters in here and let's see what we get. Good going, Samuel. It's nice to have students that are smarter than the instructor. Hey, I'm getting 0. That's good. Now let's plug in 6. See, it's going to have to be 0 too, because there's no twisting going on here. I could have put that 0 right there a long time ago. That's a roller. Rollers don't give you any twist. So if you plug in 6, let's see what you get. Minus 200 times 36 plus 2,000 times 6 minus 4,800. Boy, Jove, you get 0. Now, what we're really interested in, see what's going to happen is this thing's going to come up, peak out, and go back down to 0. That's what it does. And we're kind of interested in that point right there. That coincides with 5 meters. Let's plug in 5 meters. The bending moment at 5 meters is negative 200 times 25 plus 2,000 times 5 minus 4,800. I'm getting 200. This value right here, it peaks out at 200 Newton meters. Okay, we just did the problem 641 from start to finish. Are there any questions on that? well, I think you're equipped to do your homework problem now. You've got a homework problem similar to this. I think it's easier than this. But let me, if you're happy, I'm going to erase all this and we're going to talk about the flexure formula. Probably the most important formula in this chapter. Anybody have any last comments or questions? Well, okay, let's say goodbye to all that. Now, the topic today is bending. And what we've been doing is bending loading diagrams. We've been doing bending loading diagram and shear force loading diagrams. We've been doing both of them. But the topic right now is bending stress. The reason why we have these diagrams is so that we can find the stress. Now, there's a thing called the flexure formula. And I want to show you where it comes from. It goes like this. Ta-da, and that's it. We already know what that little guy is. That's normal stress. And didn't we discuss that on the beam you have on the top of your beam, usually you'll have compressive stress. Here, I've got a meter stick. Let me demonstrate it again here. Whoa. Okay, I've got a meter stick here. Now it's not loaded, but see, if it was supported on the ends and you load this meter stick, then it will bend. Can you guys see that it's bent? You know what? We have compression. This hurts my hands, by the way. It has compression on the top and tension on the bottom. I hope you can see that. Well, this equation tells you that. This equation will tell you that. Now this Y here, let me tell you what this Y, you know what that is, that's stress. And we just told you have compressive stress on the top, tensile stress on the bottom. This M here, well, we spent what, 40 minutes doing a bending moment loading diagram. And it was kind of hard, wasn't it? I got stuck, remember? And I had to get Samuel to help me out there. But between us, we have one good brain. Okay? So you know what that is. That's your bending moment. Now, we don't know what this is. Well, I know what it is. It's called the moment of inertia, but I'll show you where it comes from here in a minute. We got 15 minutes. Isn't that nice? But what this Y is, now on that meter stick that I just bent, it's kind of shaped like that. See, there's two ways to bend this meter stick. There's this way. Now watch. I'm gonna try to bend this meter stick this way. You ready? Get set, go. If you can see it bend, you're a better man than I am. I'll try bending it the other way. I'm not getting a whole lot of bend. Let me tell you this. It's a lot easier to bend this way. Boing, diddy, boing, diddy, boing, diddy. Or this way. Boing, diddy, boing, diddy. It's easier that way. Let me tell you this. It's hard to bend that meter stick that way. It has to do with this thing called the full name is the area moment of inertia, and we'll talk about it in a minute. I'm talking about this Y. Now, what this Y is the distance from the centroid. Now I had my meter stick kind of flat like that, right? And I was trying to bend it. But see, y is the distance. And see, if y is positive, these are both positive. So you got a negative sitting in front. If that's positive and that's positive and that's positive and there's a negative in front, well, if y is positive, then the stress is negative. You know what? That's compressive. Compressive stress is negative. You have compression on the top. Here, I'll do it again in case you've forgotten already. See, what we're talking about is when you load this thing and it sags and it bends. You have compression on the top. And this hurts my hand to do that. You got compression on the top. But see, if y is negative, going down this way, y would be negative. Now, if that's negative, you got a negative here, that's positive, that's positive. But if that's negative, you got two negatives, you get a positive. So the shear is positive. Well, positive, not shear, the stress is positive. Well, positive stress is tension. See, the stress is positive. But up here at the top, the stress is negative. Okay? Any questions on that? Well, all right. If you understand that. I've told you over and over again, but I want you to get it. Now we got 12 minutes, and I wanted to show you where this equation came from. Okay. Well, first we're going to have to come up with a little equation for strain, for normal strain. Now you've studied normal strain before. Isn't it like that? Yeah. And see, in this case here, you've got this meter stick. Now I'm going to exaggerate the curve in it. Maybe I should make it a little thicker. Here we go. Yeah, this could be the center. That could be the neutral axis, see? And when you have a thing that's bent like that, it has a radius of curvature way the heck out here. I think it goes off my board. It's up above. Oh, I just knocked stuff down. There's a great big circle there. This is called your radius of curvature. I know you've heard of radius of curvature before. And if you come all the way down, measure your radius of curvature from your neutral axis. And if you took a little teeny tiny angle, call this angle here, delta theta would be a good name for it, delta theta. Little tiny angle. Well, see, this distance right here, why don't we call that, I don't know, delta S. That distance is equal to the radius of curvature times your delta theta. That's our old friend that we know and love. There's an equation that goes like that. It goes S equals R theta. It's got a name. It's an important equation. Let me go to one of my scholars here. Let's see, somebody I haven't picked on all morning. Ben Harris. Ben Harris. Unmute and say hello, Ben Harris. Earth calling Ben Harris. Earth calling Ben Harris. Come in, Ben Harris. Uh-oh, coffee break. Brian, unmute and say hello, please, Brian.
Hello.
Hello. Hey, Brian, this equation has a name. What's the name of it?
Ooh, the arc.
That's
equation,
it?
Something like that.
Say it again.
Arc length equation. Something like
That's
that.
it. It's the arc length equation. It's an important equation. It's the arc length formula or equation. Good going, Brian. Now, Brian, one other thing. For this equation to work, that theta has to be in what?
Radians.
Yeah, it's got to be in radians or it's no good. It's got to be in radians or it's no good. Okay, now what we're going to do is we're going to write this normal strain. And in the denominator, we're just going to have rho delta theta. That's this distance here. But see, this distance is going to be a little smaller. It's going to be a little smaller. It's going to be rho minus y delta theta. And the deformation, you'd have to subtract the rho delta theta. Put that delta theta up here. From it to get the deformation, the change in your length. See this little length here is a little bit smaller. And the radius of curvature to it is rho minus y. See, here's your y. Y is the distance from the centroid. Hey, look, if you don't understand this, read the book. Now, you can get rid of some of this stuff, and here's what's left. I think this is what's left. Can you get to there with me? It's also in your book on page 241. No, 291. You could read the book. Now I got to hurry. I only got 7 minutes, and I want to show you where they get this flexure formula. But so far, so good. Now you know this. There's an equation that goes like this. It's got a name. It's named after a famous guy. Hey, Braxton. Braxton, unmute and say hello, please, Braxton.
Hello.
Braxton, this has got a name. It's an important, probably the most important equation in the whole course. What's the name of it, Braxton?
I believe it's Ohm's law.
Oh, you missed
Oh,
it.
wait.
Missed it. Try again. It's a famous guy, kind of like Ohm. That was a nice try. I'll give you a hint. Starts with H. Starts with H. This equation starts with H. It starts with HO.
Oh, it's Hooke's law.
Yeah, there you go.
Ah, my goodness,
Yeah,
yeah.
there you go. Good going, Braxton. That's Hooke's law. Now, if the strain is equal to minus y over rho, then you could write it like this. You could say the strain is equal to let me see if I can do this right. Better hurry up. I'm running out of time here. The strain is equal to, yeah, here we go. Minus y over c. Now c is the maximum value of y, okay? See, y is any distance from the centroid in general, but c is the maximum distance. You could write, instead of c, you could write Y maximum, but the book uses C for that. So we're going to do what the book does. And the strain, the normal strain, would equal to this equation. See, if Y is equal to C, then you get the maximum. And remember, if Y is positive, you get a negative, which is compression. And if Y is negative, you get a positive, which is positive. That's tension, yeah. Now, because of Hooke's law, if this is true for strain, then this will have to be true for stress. And we're halfway done with solving the flexure formula. If you can get to here with me, we're almost there. I just need the room here. Here's some room. Or you could read the book, or you can just believe the formula, I guess, if you want to. All right, here we go. The bending moment is equal to the sum of all the bending moments in your piece. And this is going to equal to the distance times the force on each little piece inside your beam. That makes sense. And this is equal to Y times your stress times your area. See, force is equal to stress times area. Oh, I've explained that before. You know that. And here is where we're going to substitute Y times, well, we got a minus Y over, something went wrong. That's a C, not an epsilon. Correct that. I made a mistake. That's a C right there. I think I just substitute for the sigma. I'm doing great. All right. Now what we're going to do is we're going to pull out the constants. So your bending moment is equal to sigma max. That is a fixed number over C. Pull that out, and you have the integral of Y squared dA. Now that, they gave a special name to it. They said that thing right there is called, oh gosh, I just don't have enough room to write stuff. That thing is called I, the area moment of inertia. I'll write it up here. It's defined that way. It's the second moment of area. That's the, some people just call it moment of inertia, but it's really the area moment of inertia. And so here's what we got so far. I need this room. Here's what we've got. We've got the bending moment. We're almost done. And I've got 60 seconds left. We might make it. We've got the bending moment is equal to, I got lost here. Yeah, here we go. Sigma max over C times Y, or I mean I, because that thing there is just I. There we go. Okay, now what? Well, I got lost. Here we go. We're going to rewrite this as sigma max. That's the maximum bending stress is equal to MC over I. I know you can get from here to here. I know you can make it. And you see that sigma max right there? What we're going to do is we're going to stick it in right here. And here's what you'll get. You'll get sigma equals minus y over c times mc over I. Oh, looky, the c's cancel out. And the bottom line is the bending stress. Sometimes they'll put a little b under there because it's caused by bending. The bending stress is equal to minus m. What happened to my y? I think I lost it. No, it's right there. M. I did that right, didn't I? Let's see, MC over I, yeah, okay. And then I plugged it in. There's that y. I left it out. It's equal to minus y over c times mc over I. Yeah. And see, the c's cancel out, and the bottom line is bending moment, bending stress is equal to minus my over I. There's our, they call that the flexure formula. And now you know what I is. It's the integral of y squared dA. Okay, well, it's sad, but our time together has come to an end. You've got some homework to do for me. And we will see you on Tuesday at 9:30, I guess. Hey, I gotta go, guys. I got another class, so here's your last chance to say anything, but speak up because I'm gonna push this red button. 5, 4, 3. Bye-bye, students.
Have a good day,
Bye.
Mr. Griffin.
Hey, have a good day.
Bye.
Bye-bye.